Welcome to all of you who are waiting for Professor S.T. Yau's rescheduled talk. This is the afternoon session of fourth day of International Conference in honor of Professor Kulkarni. Professor Yau will talk on angular momentum in general relativity. Professor Yau.
Okay. Well, thank you very much to invite me to honor my good friend, 50-year-old friend from the days when I was in the Institute for Advanced Study. And I'm glad that I could give this talk, and I'm sorry that I could not come physically. So Ravi has been, good friend since 1971 in autumn in Princeton. And he asked me to look at his beautiful thesis at that point, and I wrote a paper actually extending that work afterwards. And well, that work even published in the Annals of Math. So I'm proud that I was influenced by him. So we have been, knowing each other on and off, but not really close enough until about 20 years ago, I think. I got the invitation from him to go to the Harishchandra Research Institute in Alabama. And I was excited and was successfully convinced my wife to go with me because it's an old, deep culture that I've never been there physically. That's really a nice trip, and I learned a great deal about the culture of India. It was really fascinating to see the old places like Varanasi, which I asked Ravi to arrange it, where the famous monk of Tang Dynasty went. And that was really exciting for me to watch this. And then he also arranged me to meet this brilliant president of US in India. And we traveled together with Ravi and to go to his palace to meet him. Well, anyway, I suggest a good friendship between scientific community, between India and China to him. I think he was happy to know that, but we like to see more communication between two good countries. And then afterwards, not a while ago, my second trip to India was also arranged by Ravi. And that was rather eventful because I forgot to apply for a visa, which caused me a huge trouble. But Ravi was very powerful. He was able to arrange the trip even without visa. Well, of course, I actually need to get a visa, but I went to Shanghai and wait for the whole day from morning to night. Finally got the visa through the president of IIT. Anyway, Richard Hamilton went with me together. That was very, very interesting. He wanted to go to see the tigers, and Ravi told me to go around to see the whole India and the central India. And I gave a talk on the mathematics history of India and China. And that was, I think, it's a lot of fun. And I think I got a lot of good response during that trip. Anyway, Ravi also come to visit us at my invitation. Most noticeable was the big ICCM conference in Hangzhou, which he came. And also he came for the memorial conference for Armand Borel. And in fact, I can show you two pictures here. He is giving a talk during Borel's conference. I was in the back, and there are Dick Gross and several famous mathematicians sitting there on the dinner table. And this was in Harvard University when we have this CDM conference. So, well, time passed by fast. I was somewhat surprised when I noticed that when I was told that Ravi is turning 80. But anyway, I'm getting old too. So I wish our friendship, and indeed the friendship between India and China lasts forever. So happy birthday. So now I'm going to talk about the subject, which I found it very interesting, is the general relativity. And for here, I should mention that I was actually very touched by, influenced in a way, by the great Indian scientist, Chandrasekhar, who had been in Chicago for a long time. He invited me to give a talk there. We discussed about black hole extensively. He wrote a very important book and still a Bible on black hole relativity. So I was influenced by him. So I should mention that here. And today my talk is on the joint work that I did with my former students, Punan Chen and Muda Wang, and two other students, Muda Wang, Kera, and Wang. So two generations of my students together, we work on this thing that we call quasi-local mass and angular momentum. So it measures the angular momentum carried away by the gravitational wave when two black holes interact, for example, which they got a Nobel Prize by detecting the gravitational wave about 10 years ago. And one always believed that the angular momentum carrying away by the wave is important to how the wave behaves. But turns out even defining angular momentum is not trivial. And because of ambiguity, something called supertranslation ambiguity, which caused major difficulty to properly define what angular momentum means. And I'm going to talk about it today because I think we solved this problem, which has been about 60 years old. And we will tell you how we resolve this using the subject of quasi-local mass that we developed with Muda Wang many years ago. So let's take a look at the motivation. Newton's equation of gravity is Laplacian U equal rho, where rho is the matter density, U is the gravitational potential. As we learned in calculus, this is the equation. So by the way, all the constant that appears in this whole talk is equal to 1. Just to make life easier for mathematicians. So clearly it means I'm a mathematician when I set the light speed and everything equal to 1. Anyway, so we look at this equation. Einstein wanted to generalize this equation to make sure special relativity and gravity can combine together. So you look at this equation, want to generalize it. So what does he do? First of all, he learned from his teacher, Minkowski. Minkowski in 1907, maybe 08, discovered a very important observation that the Minkowski metric, which written in here, dx squared equal minus dt squared plus dx squared plus dy squared plus dz squared, give a complete geometric understanding of special relativity, because in this metric, photons will travel along null geodesics where length equals 0, and particles with non-zero mass travel along timeline geodesics. You can explain special relativity very accurately based on this metric. This led to a radical change in the concept of gravity to the dynamics of the geometry of 4-dimensional space-time. Previously, people thought that 3 dimensions is good enough. You just look at how things work in 3 dimensions. But this interpretation actually make it clear that 4 dimensions has to come in. And more importantly, one knows that U, the potential described in Newton's equation, has to be replaced by tensor. Because the metric coefficient is actually will be interpreted as a potential. So the potential now is replaced by the metric tensor. Now, based on this work of Minkowski and the famous equivalence principle, Einstein was looking for a tensor, which should be considered as a gravitational potential in space-time. So left-hand side will be Laplacian of the metric tensor. But then you have to make sure that it is invariant under coordinate change. That's what equivalence principle asks for. And the Laplacian of the metric, it turns out to be left-hand side. It's a Ricci tensor. And Ricci tensor is R mu nu, is basically differentiate the metric tensor 2 times and contrast suitably. So this is the first term on the left-hand side, R mu nu. But then you add R over 2 G mu nu because you want to make sure the left-hand side satisfies the conservation law. Conservation law is needed because you want to equate it to be T mu nu on the right-hand side, which is an energy stress tensor. This would be an analog of rho, the density of matter. So the right-hand side satisfies the conservation law. The left-hand side must satisfy the conservation law. That's why you need to add our 2 T mu nu. this term was actually observed by Relativity and Richard in 1901. So if Einstein actually knew this paper, he would have much easier time, but he did not. So at the beginning, he just put R mu nu. Additional minus R2G mu nu was discovered only in 1915, without knowing that it was done already by Richard and Relativity. Anyway, the left-hand side can be interpreted as Laplacian or the metric tensor in suitable coordinate form. The right-hand side is a matter tensor. So that's how the Einstein equation comes up. So, so this is relating gravity with matter similar to Newton's equation, the Einstein equations, where similar to Newton's equation. That's why in the case that light speed is going down to 0, it recovers Newton's equation, because that's exactly how it was modeled after. In space-time, particle with mass travels along geodesic, which are timeline, and photons still travel along null geodesic, because the metric tensor will give rise to geodesic. So you have all these concepts, and you still have the similar picture like Minkowski. And Einstein equation shows that rigid curvature of the space-time matter accounts for matter distribution, but the content of gravitational force rests on the full curvature tensor of the metric. So rigid curvature accounts for matter, but the full curvature tensor accounts for gravitational force. That's how things come out. So we have to understand the full curvature tensor to account for the phenomenological description of gravity. So Einstein equation is great because it gives the equation, but on that hand, we have to understand the dynamics based on this equation. There are many important problems that come up because solving equation, you cannot just solve the equation. The equation gives you a local control of the space-time, but global control depends on asymptotic behavior and infinity and all that. So we are dealing with asymptotic behavior globally now. Global geometry comes in. So, well, first of all, there's a very important question which arises already in Einstein's time and also in Hilbert. David Hilbert also worked in general relativity, as we all know. The first thing that they encounter is how to define mass. Already, he knew, Einstein already knew, the density dependent on gravity would depend only on the first order differentiation of space-time metric, but the choice of normal coordinate will render such a measurement trivial at a chosen point. Given a point, you can always choose a so-called normal coordinate so that the first differentiation of space-time metric is equal to 0. Therefore, whatever you define for matter density, it has to be 0. Because the equivalence principle said that nothing should depend only on the choice, special choice of coordinate system. So therefore, we have difficulty to define what a matter density means in general relativity. Matter density, not matter density, density for gravity alone cannot be defined as a result. So instead, we try to associate conserved quantities to a space-time region bound by two surfaces. So we therefore, since there's no density, we try to go to something which is still acceptable, namely the energy, gravitational energy within a two-dimensional surface. The importance of such a notion was actually started by Roger Penrose, who leads the search for definition of the quasi-local mass and definition of quasi-local angular momentum already as a #1 and #2 problem in his famous paper in classical general relativity. This paper appeared in Seminars Differential Geometry at my invitation, published in Annals of Math Study in 1982. He leads several important problems, some unsolved problems in classical general relativity. So these are very important problems. Now, why are we interested to search for the concept of gravity? I mean, within a region. Well, the problem is that in order to make important statements, for example, binding energy, we need to know something quasi-locally. Two bodies interact with each other, and you want to know its binding energy. So usually what we do is that we take the energy of one body add up with the energy of other body minus the total energy of the whole thing. Now, during the Einstein's time or Hilbert's time, the only concept we know is the total energy. So we still need to know the local energy for one body. So therefore, we need to know definition of quasi-local energy. And a good definition of quasi-local mass should also help to control the dynamics of the gravitational field, because we like to see everything is independent of choice of coordinate. This will complement the energy method in hyperbolic equations. Einstein's equation is a hyperbolic system of equations, and the major tool in hyperbolic equation is to devise something called energy method. But the energy method they use in hyperbolic system depends on choice of coordinate. It's not physical. We need to find something which is more physical to understand dynamics of general relativity. So this would be important, I think, the quasi-local energy. So far, it has not been used by the workers in this field yet, but I think it will be. Okay, so what are we trying to do? What we try to do is that we want to associate a two-dimensional surface, space-like surface, not space-time, two-dimensional space surface, which is a topological sphere, even with the boundary of a three-dimensional space-like region. We will account to the total energy within that two-dimensional sphere inside the three-dimensional region. This is the concept we are trying to do. So this has been tried for many, many people for last 50 years also. Only about 15 years ago, Wang, my former student in Columbia now, worked out a concept which depending only upon the extrinsic and intrinsic geometry of this two-dimensional surface. We can work out this concept. I think it's successful. We make the assumption that the two-dimensional surface is space-like, which means the induced metric on this two-dimensional surface is Riemannian. In addition, we assume the surface has space-like mean curvature vector. So mean curvature vector is a concept appear in geometry, and we want it to have length strictly positive. This is a concept we make assumption of. Without this assumption, many important properties of the quasi-local mass fail. So we need to make this assumption. Now, how do we? Now I'm trying to tell you how we define this quasi-local mass. So space-like two-dimensional surface has a normal bundle. The normal bundle is a rank 2 bundle because you're sitting in a 4-dimensional space-time. The rank 2 bundle has some condension form because the induced metric from the ambient space has a condension form. So I'm defining what the condension form is. We choose a frame on the normal bundle. Namely, I take the mean curvature, normalize it to be unit 1. So that's x divided by mod x. And then because the Lorentzian signature 1, 1, I can find another vector j, where j divided by absolute x is a future timeline vector given by reflection of the mean curvature vector through the incoming light cone. So I have two normal vector, x mod x, j mod x, and this is what we define here. And then I use the normal connection to differentiate it, and this defines a one form, connection one form on the normal bundle. So this is something depends infinitesimally on how the surface is sitting in the ambient space-time. This is a quantity I need to define quasi-local mass. So what do we have now? We have three quantities, a triple. Sigma is a metric, induced metric. X is a mean curvature vector. Alpha x is a condension one form. So this is a triple that we have. So sigma x alpha x is a triple. Given this information, we work out an energy associated with it for any isometric embedding of the surface sigma into Minkowski space-time. So what we do is that we embed the sigma into Minkowski space-time, and this gives rise to an embedding, and I have an energy associated with it, and I'm minimizing the energy, and I will get an image surface called sigma naught, which has same induced metric as sigma, but now with new mean curvature and new condension form alpha h naught. So then we compare the extrinsic geometry of sigma with extrinsic geometry of sigma naught. Sigma is sitting in the space-time, physical space-time. Sigma naught is sitting in Minkowski space-time. So now out of these these 5 quantities, sigma is the induced metric, H is the mean curvature vector, H naught is the mean curvature vector sitting in Minkowski space-time. Alpha H is the condensation one form in the original space-time. Alpha H naught is the condensation one form on the induced Minkowski space-time. So these are the given quantities out of the triple that are given to you. Well, given such a thing, it turns out we have an interesting quantity that we can associate with now. Now we are sitting in R3, 1. R3, 1 has many symmetries, namely translation symmetry. There, I take a constant vector, which is timeline. I take a timeline constant vector in Minkowski spacetime. I take an observer traveling along this timeline vector, timeline straight line, which is timeline. And given this, I look at my embedded surface and I measure the time associated to this embedded surface. So sigma naught is sitting in R3, 1. I travel along the straight line and measure the time, which we define with tau equal to minus x dot t. T is the timeline vector, constant vector. X is position vector. So it's a height function in geometric terms. I look at the height function in the embedded surface. Tau would be the important quantity. Is kind of like the time that we see in the model space. Now then I define these 2 functions, low and j. So low is very simple. I measure difference between the mean curvature in the Minkowski spacetime minus the mean curvature in the spacetime, but distort by the tau function, by the time function. And so it's defined in this way, low. And then I take j, which is defined this way, which let me not go into detail of that. So what is that? These are, first of all, low is a function defined on my original surface, sigma, and j is a vector field defined on sigma. So what do I have? I have low and I have j. J satisfies the equation, which is divergence free in our surface. So divergence JA equals 0, and the metric is sigma. So this is what I call the optimal isometric embedding equation. So I can solve this equation in general. One can prove that it can be solved. So you can use computer to solve it to find the solution, but we cannot solve it in closed form, but it's good enough for all purpose. So what do I have? So remember, I have H and I have H naught, and I solve the equation. This H naught actually, H naught and tau, both of them can be solved by look at this equation that I wrote down here, the optimal isometric embedding equation. This turns out to be a nonlinear elliptic equation. So if you don't like the concept of isometric embedding, you could forget about it. You just solve this equation. It's a 4th order elliptic equation. We solve it. And then we define the quasi-local mass by the bottom equation. The total and the quasi-local energy is simply integral low over the sigma. Now this turns out to be positive for our space-time. So the energy we define is positive, and it's equal to 0 if the surface is sitting in Minkowski space-time. So this energy is very good. It is trivial for any surface sitting in Minkowski space-time, and yet non-trivial and positive when it's not. And also it satisfies some important condition, namely it will recover the total mass that physicists has been used since Einstein's time. It's called ADM mass nowadays, and also called boundary mass. We will describe it a little bit later. So recover everything that we know of. So now I define to you what quasi-local mass is in this way. Well, this quasi-local mass concept was actually developed for the last 50 or 60 years by many people, and a very successful, important concept was discovered by Wang-Yau, and we Marisa Liu and I generalized it to more general situation later. But all of these things are actually pretty good, but it's not quite the right one because this is not equal to 0 when the surface is sitting in trivial space-time. So it's too positive. It is sitting whenever it's supposed in Minkowski space-time, you are not supposed to encode any energy. But yet this definition gives more than what you need. So only when I did with Wang, the definition allow us to prove that it's strictly positive in general, but 0 for surface in Minkowski space-time. So it's exactly the right one. Now this embedded surface turns out to be unique in the Minkowski space-time that best matches the physical surface sigma. When the surface is very close with round, this turns out to be rigid. Very good information. For perturbative configuration, namely when the surface is very close to sphere, we can actually calculate this optimal isometric embedding. We can solve the equation perturbatively. So it's very good. We can calculate it when the limit goes to spatial infinity, then it recovers something called ADM mass. When it goes to null infinity, it recovers the boundary-Trautmann's mass. So this recover all the important quantity that is known to work well. So we are pretty happy that it finds out. This is a very good definition. So let me say that in the old days, what people do is the following thing. This is going back to Einstein himself, as I said. So you take initial data for the space-time, which means that you are given G, which is the metric defined on the three-dimensional manifold, and K is like the dg over dt is the second fundamental form of the free manifold sitting in the space-time. So initial data for Einstein equation has two data, G, the metric, and also the dg over dt, which is captured by second fundamental form in space-time, G and K. So in the old days, during Einstein's time and Hilbert's time, you said, okay, let's assume G at infinity is equal to delta function, which is the Minkowski data. G minus Minkowski data is asymptotic to 0. So distance to the power minus P. And the second fundamental form K is going to 0 and infinity also out to the power minus Q. So in order to define the mass, they write down this quantity, integral of S2, Gij, comma Gj minus Gjj, comma I. This is the integral, and clearly you want it to be convergent because we are taking limit to infinity. And in order to do it, Einstein and several people later make assumption that P must be big and Q must be big. The optimal size was P bigger than half and Q bigger than 3/2. That has been used all along to make sure the things are well defined. Now, this concept turns out is well defined in the sense that it's independent of choice of how the sphere goes to infinity. This was proved by my former student Robert Barnett in Australia. And then afterwards, well, actually before that, Rick Shen and I proved this mass is strictly positive. In 1979, we proved this positive. It's called positive mass theorem. And 2 years later, Ed Witten used a different method to prove the same thing. So this is 40 years ago now. Now the limit of the quasi-local mass calculate the ADM mass as I defined, assuming this classical asymptotic, where P is strictly half and Q bigger than 3/2. But for more general asymptotics, it was not known because it diverges a priori. But because our definition is quasi-local, we have no convergence problem. And then we define it and take limit, it turns out it's good, even when P is not strictly bigger than half or Q strictly bigger than 3/2. This allows you to capture more physical meaning of the data. This is the reason is that the optimal isometric embedding equation is actually good. That helps us a great deal. Okay, so now let's go to null infinity. This is infinity where we, as an observer far away from a black hole, for example, we are sitting far away. We want to see how the black hole works. Well, what we do is that we watch the light ray travel along null geodesic coming from the black hole. So we are watching something called null cone. And this description is called null infinity, is for an isolated gravitational system, was first described by Bondi and Sachs in 1962, and actually was described by Troutman earlier in some special cases. So sometimes I call it Bondi Troutman mass. And then later in 1965, logic panels do a conformal compatibilization that has been used all the way up to now by most people in physics. And then in 1993, Quasilocal, Kleiman wrote their famous paper on stability of Minkowski spacetime. They found out some important properties which does not satisfy what Bondi, Sachs, or Penrose wants. So the Bondi, Sachs, and Penrose formulation is very ideal. It implies the spacetime has something called peeling property, namely certain curvature tensor will go down to zero in a suitable frame. And this is not true in general, turns out, demonstrated by the work of Quasilocal and Kleiman. So one should be careful when we use the Penrose diagram, because one has to be, it's not clearly true. First of all, the regularity of the Penrose diagram has to be very carefully handled. But anyway, for convenience, we still use this concept given by Bondi and Sachs. And Bondi and Sachs, which I will write down the formulation immediately, they assume all the coefficients they have has an asymptotic expansion near infinity in terms of 1 over R. And this was generalized by Kushel and several people in 1995. Now, so let me see what we can. Yeah, we are now studying dynamics of the space-time now. So dynamic space-time, we use U and V U coordinate, which measures the things traveling at infinity. And so U and V are functions, and so is HAB, WA, and WB. So we write the space-time, the Minkowski space-time metric in this form. If U, V equal to 1, when U and V equal to 1, and HAB is the standard spherical metric on the Euclidean sphere, and W equals 0, this will recover completely the Minkowski metric. So what Bondi and Sachs say is that, okay, we model after the Minkowski metric near something called null infinity. And we look at U and V, which has a property that UV is close to 1, HAB is close to the sphere metric, W close to 0 when R goes to infinity. But they normalize the fact that HAB is equal to determinant of the Euclidean metric. Okay.
This U and V, do they have some physical significance?
Wait. Just wait. Let me see. Yeah.
This metric tensor that you wrote down, this U and V, and do they have some physical significance?
Oh, yeah. Exactly. The mass will come out from U and V. Well, I'm going to explain to you the physical significance now. Okay. The Bondi mass and all this come out from U, expanded U and V and all this. You will see immediately. Okay. So right now. Okay. Now remember V. V is here. V is the first quantity, U and V. Okay. So Bondi and Sachs write it to be V equal to 1 minus 2MUX over R plus big O R minus 2. X is a point on the two sphere. Okay, on the two sphere. So MUX is so-called mass aspect of Bondi-Sachs mass aspect. The integral of 2MU is the mass, the Bondi-Troutman energy momentum vector, the energy, and PKU is given to you the linear momentum, 2MUX times X tilde. X tilde is the spherical coordinate. And then you put them together, I define 4 vector, E comma PK is the Bondi-Troutman energy momentum. So this is the physical meaning of the V. Okay. But then I'm going to talk about the physical meaning of HAB, U, and W also. Okay, that comes in angular momentum. So for defining energy momentum, it becomes reasonable, easy, just write it down. Okay, and it's important that we know this energy, E comma PK, is a good vector, namely E is positive. This statement that Bondi-Chalmers energy is positive. Okay. Now, Bondi derived a very important equation. He differentiates E respect to U. U is the movement of the null cone. And he found out is equal to -1/4 integral n squared, norm n squared. So I'm going to define what n is to you immediately. Namely, in the bottom, you look at this. What we do is that I take the metric tensor HAB, define the sphere. I'll make it to be equal to Euclidean metric, the sphere metric, sigma AB, plus lower order term, 1/r CAB plus big O R -2. So CAB is a distortion of the sphere at infinity from the sphere. So C, okay? CAB is a tensor measuring its distortion from the standard sphere. And then Null's function is the dynamics of this sphere. So CAB differentiates to the U. This is called Null's function. It's actually Null's tensor. Okay. So from HAB you recall in here is the metric defined on the two sphere. And from here, I define two quantities. CAB is a distortion from standard metric, and NAB is the rate of distortion. So NAB is a Null's function. So it turns out it's very important. Differentiate the Bondi energy is equal to integral or the norm square of it. So the energy always decreases. So what that means is that it carries energy away, which means that the energy decreases, and how much it decreases is the energy radiated away from this whole interaction. So E infinity, U go to infinity, U go to -infinity. The difference is a flux. The flux of the total energy give rise to -infinity to infinity integral n squared. This can be defined to be the total energy carried by the gravitational wave. Okay, so that's how it comes out. The total energy carried away by gravitational wave is integral from -infinity to infinity or integral n squared. So n is a distortion of the sphere. Now, on the other hand, this now infinity, as we see it, has a symmetry group, a big group. It's called BMS group in memory of these three Nobel physicists. And there are coordinate transformations at now infinity, which keep the Bondi sex coordinate form. Okay, so in other words, you take a coordinate, transform U, transform all these things, you move it around, but you want to make sure you still have a Bondi sex coordinate form. That's what it calls the BMS group. Okay, but on the other hand,
yeah, in terms of Lie groups, is it some SO4, 2 or something like that?
Oh, no, it's an infinite dimensional group. Infinite dimensional. It's an infinite dimensional group. Okay, including diffeomorphism.
But some sections of the
defines a diffeomorphism group. Okay, and then there's a big group of translation. So we don't have a preferred coordinate system in the general spacetime. So we have to understand what that means. So a very important subgroup of this is you move U by function defined as S2, U bar plus Fx. Okay, you simply move the U by function. This will make sure that the Bondi sex coordinate will go to another Bondi sex coordinate. This subgroup of the BMS group is called supertranslation. So already you see there's an infinite dimensional group sitting there because F is arbitrary, smooth, arbitrary function. So that defines an infinite dimensional group. Okay, so we want to understand all the interesting physical quantities under this group, this big group action there. especially under supertranslation, because a major infinite dimensional part comes from this supertranslation. And we want to understand what the mass changes and the shear tensor and all these changes. This becomes rather complicated, turns out. But the transformation of the new tensor actually turns out to be reasonably simple. That's what we know by doing direct calculation. On the other hand, it turns out the total energy radial away compared U coordinate is the same as the one that we compare U bar coordinate, because there's some divergence that we can integrate away. And so there's no ambiguity to define what it means for the total energy radial away. Okay, so that's good. Total energy is independent of choice of the coordinate. And this is very important. In fact, we can recover this by taking the limit of the quasi-local mass that Wang and I define. We take the sphere along the now infinity, take the limit of the quasi-local mass we define, we recover the boundary Trautmann mass. So that's good. The reason we can do this calculation is because for the two-dimensional surface on the now infinity, the optimal isometric embedding has a unit solution, and we can calculate it perturbatively. So there's no problem. And we can also prove the boundary Trautmann mass non-negative in this way, because we know the quasi-local mass we define are non-negative. As a result, we give a rigorous proof of the fact that boundary Trautmann mass is non-negative. This was proved a long time ago, but actually with very strong assumptions on fall-off condition and all that. And the proof is very non-trivial in the other case. Anyway, we do that well, and we have no problem. The reason is that we need this one because when we have dynamics, the now infinity is very rough, and everything is can change things around. And the important thing is that we do not need any peeling structure now infinity, which was assumed in most of the calculation of boundary mass, because they assume there's a Penrose diagram. And the Penrose diagram, as I said, is not quite true, as was demonstrated by Quasilocal and Kahneman. The peeling structure is not quite true. So our proof actually does not depend on it. So they work out nicely. Now, the definition of angular momentum turns out to be much, much more subtle. This has been an open problem for close to 60 years. Since 1960s, people ask this question, how to define the angular momentum in a correct manner. And I list down quite a few workers, and I probably miss out some others. And all of them has done very beautiful work, but nevertheless, it is still depending on the choice of supertranslation, depending on the boundary flux coordinate. And this is not satisfactory because we don't want a quantity to depend on choice of coordinate. Now, I will mention in particular this work of Dre and Schwaber. They, for U cut, that means U equal constant, you write down this condition. So NA minus half CAB. CAB I already defined to you is a shear of the distortion of the regular metric. So you know what CAB is. What is NA? And also YA. Y is a rotational killing field on the sphere. So you know what that is. NA comes out from WA. You recall what WA is. Let me recall to you WA. WA is sitting here. Is in this metric, there's a WA sitting in here. dxa plus WA du. Okay, so now finally we use WA in the angular momentum. So angular momentum is very subtle, delicate quantity. We write down WA in this form, and NA appears in the 1/r cube term. See, so angular momentum go down to lower order term, 1/r cube term. So we define NA in this way. This defines you a interesting quantity that appears in most people's definition, and is sometimes called mass angular momentum aspect. Okay. Okay, so this is what they define, and under very restrictive assumptions, they can prove that it's good. But according to Roger Penrose, the very constant angular momentum gets shifted by these supertranslations in general, and this annoying, he said, it's hard to see in these circumstances how we can rigorously discuss such questions as the angular momentum carried away by the radiation. So this is a very important question that we encounter now, especially now that we know we have observed the radiation as was demonstrated about 7 or 8 years ago by LIGO, that we know radiation was observed. And now we want to get more interesting quantities to be observed, and angular momentum is certainly one of them. But now we don't even know what that means, so we have to define it correctly. Okay, so now what we want to do is this. We choose and we take an angular boundary sex coordinate related to another one by supertranslation F. So U bar equal U plus Fx. Then what Penrose really about is that you define the flux from minus infinity to infinity, they may be different. So delta F or delta J tilde means the flux. The angular momentum at minus infinity to plus infinity, we want to make sure that flux is independent of choice of angular coordinate. So how does it depend on the supertranslation ambiguity is what Penrose was really about. Well, so what we found out by the group that we mentioned, Muda Wang, Kat Wang, and Punan Chen, and Kela. So we proved that we demonstrate that if the new function, new tensor decays suitably, which is needed in order to make quantity to be finite, then if the boundary sex coordinates are different by a supertranslation called F, then the difference of two flux can be written as the integral of this following form. Now, what is F? F is the supertranslation, is a function. A function defined a sphere, have spherical harmonic expansion. We take the lower order mode, which is linear, and the constant part of this function. So I write down F, L less than or equal to 1. That's what it means. I take a spherical harmonic expansion. I take the first two modes. So these are linear function plus a constant times this right hand side. Ya is the rotation vector field. Del A m plus m minus m minus is the flux of the mass aspect. We got this formula. This is a very good formula. Why? Because this actually tells you the following formula. Before I go explain this one, let me tell you how we come up with this angular momentum definition. So in general, what we do is that we take a vector field, Killing field in R3, and then we use the optimal embedding, and we define a corresponding quantity in this way. So T0, Y is the time function that we defined before, time function part of Y, and multiply rho, and then plus JYT. This basically come out from Noether's current argument. This is supposed to write quantity, conserved quantity. And so in particular, quasi-local angular momentum is JYT, because T0 is perpendicular to the rotation. So only part is the last part. This angular momentum actually satisfies many interesting important quantity when it's defined quasi-locally. What we do is that we take this sigma and let it go to infinity. This one is well defined because sigma is finite. Now notice that when we define the quasi-local quantity, it's very complicated because we have convergence property here. And the convergence property has bothered many people, and this makes it to be difficult to be defined even. But what we do is that we define quasi-locally first, and then we take limit. So there are many interesting properties can be washed, difficult problem can be washed out by doing that. So that's how we did. Now, important part in terms of computation, we show it to you. We compute the limit of quasi-local angular momentum in boundary coordinate explicitly. So this is not just talks, we actually compute it. We compute the shear function, the distortion of the space of the two-dimensional sphere, and we decompose it. It's a tensor. We can use a Hodge decomposition. We found this formula, which we write down here. The important part is that on the two-dimensional sphere, we found a potential, which is called small c. So small c is the important function that appears in decomposition of CAB on S2. Well, then it turns out in our calculation, the angular momentum associated to the rotational killing field is come out to be the following form, where the first two parts is very similar to other people had. They have NA, we have NA, they have CAB del covariant differentiation CDB, we have that also. The coefficient is a little bit different, but these two terms are the same. The major difference is the last term. C has never appeared in any other previous definition before. So in a way, it is a little bit funny because small c is not local, but it's defined on the S2. This is non-local quantity appear in the surface term, surface metric, and this probably is the reason why this was not found before by other people. We found out this small c is there and would help you tremendously in doing the calculation of ambiguity. So what we found is the following thing, that we rewrite what we just said before. Under a supertranslation, the total flux of the angular momentum is changed in the following way. The difference going to different ambiguity is coming out from the total flux of the linear momentum. And this is what you expect to be true, because total angular momentum will be changed even in classical mechanics. Classical mechanics says that angular momentum will change when you move the center of mass around. And so therefore, it depends on the linear momentum of the whole configuration. And this exactly says that the total flux of the angular momentum is shifted by the linear momentum. So this is exactly what we expect in special relativity. So I think this beautifully solves the problem of the ambiguity of supertranslation to define the angular momentum. So in conclusion, I would say that we have found 10 conserved classical quantities, the linear momentum, the energy, and J, the angular momentum, and the center of gravity, which appear also. And we have these 10 quantities, and this set is, this will, first of all, the definition we gave will vanishes for any boundary sex coordinates system of the Minkowski spacetime when there's no gravity. Now, this fact is actually non-trivial already, because in all the definitions that we know of, they are non-trivial, even in Minkowski spacetime. But we do, they are equal to 0. And in the K metric, which is a very important thing, the linear momentum and the center of gravity vanishes, but energy and the angular momentum recover the mass and angular momentum of the K metric. The K is one of the most important space-time recover the rotating black hole, so that's very important to recover it. And then we also prove that it satisfies the basic physical law under ordinary translation. So this seems this very good. This includes quantities. Of course, we can actually define more than this, depending what kind of vector field we choose in space-time, in Minkowski space-time. But I think this is pretty satisfactory. So, well, thank you. I finished this talk, and I congratulate Ravi again for happy birthday. Yeah. So, any questions?
Hello. Yes.
Right.
No, Shastri, is Shastri around?
Yeah.
Shastri.
Hello. Can I ask
Yeah, Shastri is in the chair.
Yeah.
Sorry, there was some problem.
Okay.
So
Hello?
I'm inviting questions.
Yes.
Yeah.
Yeah, I have a question. Do those
Yeah.
properties uniquely determine the quantities?
Yeah.
On your final slide, you list the various properties that are satisfied.
Right.
Do they uniquely determine those conserved quantities?
Oh, well, that's an interesting question.
Maybe you should
The mass.
show your slide, last slide.
Last slide. Well, the mass and the linear momenta alone probably do not uniquely determine the thing that we have, because there is a different definition given by my former student, Robert Barnick, on defining E and PK. But he could not define J and C in our way. So that's quite possible that these four quantities uniquely determine this, this whole theory. But I could not tell at this moment. But an interesting question. Yes.
Yeah.
Thank you.
Any other
Why is it called quasi-local rather than local?
Well, local means that you have a density. That's how we define it. Define it. We do not have a density to integrate about. So in fact, if you take a small sphere going to limit, you will have a asymptotic expansion. The cubic term corresponding to matter density. Cubic term is matter density. And then when you expand again to R to -4, R to the power 4, R to the power 5th, the gravity part appears in the R to the power 5th term. So in the definition of quasi-local mass, the R to the power 5th term appears to be a curvature tensor, which is called Bell-Robinson tensor. Okay. So Robinson tensor, Bell-Robinson tensor appear, but it's in R 5th term. That's why there's no density, because if no matter, then only R 5th term appears, so the density will be 0. But it's there in the higher order term, lower order term.
Any other questions?
Yeah, so there is a question in the chat box.
Yeah.
That's
And-
fine. That's probably a silly question.
Yeah.
Just curious whether the ambiguity is might vanish for some subgroup of super translations.
Well, I mean, you take a smaller subgroup, you can probably always make it vanish, but we want to make sure it's
A
independent.
large
choice.
group, yeah.
Yeah, there's a huge group, there's an infinite dimensional group.
Yeah. Right, because I thought the point was for the ambiguity to disappear.
Well, it's like in general relativity, everything should be independent of choice of coordinate.
Right.
The group of diffeomorphism appears.
Mhm.
So
Thank you.
do we have
No, is there, is there some large compact or even non-compact Lie group, which is a homotopic to this large group that we are talking about?
Well, I mean, we have more or less, we have a Lorentzian group sitting there, but the
Yeah.
huge group is infinite dimensional, is probably contractible down to there.
And so SO31 is there, but
Yeah.
is also some conformal compactification you mentioned.
Yeah,
So
the
it's-
conformal compactification is not, as I said, is not quite right, and the
I
Penrose
see.
compactification.
So it's
I
SO42 is not
don't
there.
want to. I don't want to use the Penrose compactification because I think it's not
Yeah.
there.
any other questions?
Also, Penrose compactification makes sure regularity, which is very strong.
Yeah.
Any other questions or comments? Big thanks, Professor Yau. So let us
Yeah.
thank him for.
Thank you. Happy
Thank you.
birthday again.
Yeah, thank you,
Lovely.
Yao.
Yeah, bye. Hope to see you here sometime.